All right, so last class we talked about the atomic history, some basics about the atom, and then we arrived at the Rutherford model, which had two problems. Okay, the first problem was how can the nucleus stay together? Now that problem was solved with the discovery of the the neutron. The second problem, so how do electrons not fall into the nucleus, thereby destroying the atom? So we're going to attempt to answer that question today. All right, so but before we can address that, we need to learn something about light first, the photoelectric effect, photons, and then finally, with Niels Bohr, we can then answer that question. All right, so here goes. Let's start with light. This is quite a basic question. What is light? All right, many scientists and philosophers have stumbled on this question. How do you explain what light is? So there are some answers throughout history. So a long time ago, at 300 BC, the Greeks, they thought light was just a stream of particles that you just happen to see with. And later, Isaac Newton, probably the most successful and famous scientist of all time, he proposed that light is also a particle. Now keep in mind, this guy is extremely smart. He discovered the laws of motion. He discovered gravity, came up with Newton's equations. He invented calculus at the age of like 24 or something like that, basically because somebody dared him to. So this guy is a mad genius, all right? He was the one that used a prism and separated white light into the rainbow. So he explained what a rainbow was. And this guy is saying that light is a bunch of particles traveling in a straight line. Now, near the same time, you have another scientist, Christian Huygens. He proposes that light is a wave. Okay, just like water wave, a sound wave, light is a wave, not a particle. So what is it though? What is light? Is it a particle or a wave? So finally, it's been settled in the mid-19th century. So James Clerk Maxwell, another famous physicist, he came up with the Maxwell equation. Okay, the Maxwell equation basically shows you that light is an electromagnetic wave. Now, what does it mean by electromagnetic? Light is essentially an oscillating electric and magnetic field. So in physics, if you have a changing magnetic field, that will produce a current, which produces an electric field. And an electric field will produce a magnetic field. And that magnetic field will then produce an electric field, and so on and so forth. So it kind of complements each other and start creating alternatively electric and magnetic fields. And this oscillation travels at the speed of light, and that is light. Light is electromagnetic wave or electromagnetic radiation. Okay, and it has many different wavelengths. It goes from radio waves with long wavelengths to gamma rays with really short wavelengths. We can only see a tiny slit on the electromagnetic spectrum. That tiny slit we call the visible spectrum. All the other lights, like infrared, ultraviolet, we cannot see with our eyes because our eyes are not evolved to detect those lights. So, okay, so light is a wave, all right? According to Maxwell's equations, which are really good, yeah, it's a wave. But it's not over. It is soon discovered that, hold on, there is a problem. This effect, called the photoelectric effect, it basically says if you have a piece of metal, you shine some light on that metal, electrons will be displaced from that metal. Okay, so light can knock electrons off of an atom. Okay, cool. So that's interesting. So we call it the photoelectric effect. So what's the problem? Well, the problem is the intensity of the light doesn't really matter. It does not change the speed at which the electrons are knocked off. All right, so what that means is you have a piece of metal, you can either shine a really dim light and you observe that electrons are moving. Okay, cool. It has a certain kinetic energy going in that direction. Let me turn up that light. Let me turn the dial and amp it up. So now I have this really bright ray of light, but same color, same frequency. Let me observe that electron. So logic and classical physics would tell us that will travel a lot faster because now you have a more intensive light, right? It's kind of like playing billiard again. If I poke the ball, it should go forward slowly. If I really poke the ball hard, the ball should go up quicker because you have higher energy. But that's not what's observed. If you turn up the intensity of the light, the brightness of the light, in other words, it did not affect the speed of the electron ejected. What did? The frequency of the light. In other words, color, because color depends on the frequency of your wave. So there is a difference between a red light, green light, and a violet light. Their intensities don't really matter. All intensity does is you increase the amount of electrons ejected, but it did not increase the speed of the electrons ejected. Okay, even a really weak violet light made electrons travel faster than the strongest red light, the more intense red light. So that makes no sense whatsoever. How do you account for the color having an effect on the speed of an electron, but not how many light actually hits that electron? That makes no sense. Well, so a new branch of physics was needed to explain this. So in the 1900s, what's widely regarded, or who's regarded Max Planck as the founding father of quantum mechanics, because he discovered the quantum. He discovered that energy was not a continuous stream. What does that mean? That means energy, such as light, exists in tiny packets of discrete units. Okay? You can't have anything between the discrete packets. So a quantum is just a unit of energy, and the plural is quanta. It's kind of like money. Okay? Money is not continuous. You have discrete packets of money. The smallest unit of money is 1 cent, a penny. Okay, Canada banned the penny a couple of years ago, but if you go to the bank, you can still see pennies, decimals in the bank. It's just that when we actually take the money out and use them, we round to the nearest 5 or nearest 10. But the smallest unit is the penny. You can't go smaller than the penny. Okay, so same thing with energy. There's the smallest packet of energy that you can have. You can't go smaller than that. So that's what Planck discovered. And this equation was also discovered. E equals NHF. Now, N is just any integer. It could be 1, 2, 3, 4. Energy is E in joules. And then F is the frequency of the light. And H is a famous constant called Planck's constant. So what this equation is trying to tell you is energy E is proportional equal to blah, 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 F. Okay, energy is frequency. So they're directly proportional. If you increase the frequency, you will increase the energy. Now that makes sense because that's what we observed. And then later, Albert Einstein applied Planck's idea to light, and then he used that to explain the photoelectric effect. So what Einstein said, well, a photon is a unit of energy. Light is not only a wave, light is like a particle. So we went full circle. Okay, we go back to the model that light is a particle now. A photon is just the smallest unit of light. And if a photon that has enough energy collides with an electron, the electron will absorb that photon and its energy, and it will be ejected from the atom. So how fast that electron moves depends on how much energy that photon has. The higher the energy of the photon, the faster the electron will be. Now, what does the energy of the photon depend on? E equals to HF, the frequency. Okay, so according to Einstein, the photoelectric effect makes perfect sense. Increase the frequency, change the color of the light, you increase the amount of energy that the light has, which means the photon has, And then more energy will be absorbed by the electron, means it will move faster. Okay, so the photoelectric effect demonstrates that light is made up of photons. Light behaves like a particle. Hold up, does that mean light is not a wave? So Maxwell was wrong. No, it does not mean that. It means that they're both right. Light is both a particle and a wave. It has both properties. We call this the wave-particle duality. That seems ridiculously weird, but yeah, light is both a particle and a wave. And we will learn tomorrow that electrons behave the same way. So here is a video on the photoelectric effect. All right, so given the photoelectric effect, so we are ready to explain why electrons don't fall into the nucleus. All right, so protons are positive, electrons are negative. According to the laws of physics, they should spiral in, but it doesn't happen, so why not? All right, the fact that atoms are stable and they don't collapse, as predicted by this problem, suggests that electrons don't lose energy as it goes around the nucleus, okay? Kind of like planets going around the sun, we're not spiraling into the sun, okay? We're not losing energy going around the sun. So this must also mean that electrons behave similarly. They don't lose energy, but why not? How? So Niels Bohr answered this question. To understand what Niels Bohr did, we have to first look at spectroscopy. What is spectroscopy? Basically, it is analyzing the spectra of light from a certain source. Here's how it works, okay? So when light passes through a sample of anything, the light will be absorbed by some atoms in that sample. And when the light gets emitted again, you take that light, you put it in a prism, it will diffract into its rainbow colors. Okay, now the thing is, you're not going to get a full rainbow because some of that light is absorbed by the atom and the atom only emits certain colors of light. Now this is important because every single atom on the periodic table, they have their own unique spectrum of light that they emit. It's like their fingerprint. Different elements will emit different wavelengths of light which correspond to a unique color. So by reading which colors were emitted, you can deduce what element absorbed that light, so you can now know what that element is. Okay, does that make sense? And then you will have an instrument to just detect the light. Based on the spectrum, you can determine, oh, so the light passed through helium, let's say. And the spectrums have different types. You can have an emission spectrum. It is the radiation emitted by an atom. So atoms can emit light when their electrons fall from a high energy to a low energy. So light will be released. And different atoms will release different spectrum, but they're going to be the same spectrum for the same atom. So this is an emission spectrum. A continuous spectrum is just all of the colors of the rainbow. Just take light, put it through a prism, you will get the continuous spectrum. All right. So a line spectrum will be, well, you take light, you shine it through, let's say, a gas, and then the gas will absorb some of that light, excite their electrons, so their electrons would jump to a higher energy level and then fall back, so releasing energy. And that light released by the atoms will then be put into a prism, separated. You can see what color they are on a detector. And then you can study this pattern, you can study the wavelengths and use that to determine, well, what element did that? Because every element has its own fingerprint and we know what the fingerprints are. So we can produce a unique line spectrum and use that to tell what element it is. So that's how we know what the sun is made of. The sun is made up of hydrogen and helium. How do we know that? Because we study light from the sun using this process, and we found the line spectra for hydrogen and helium. Okay, some carbon. That's it. Nothing else. There's nothing else in the sun because that's what the light tells us. So using spectroscopy, the idea that you can separate the light from an atom to figure out what element it is, this gives you a big clue of the structure of the atom. So this is hydrogen in the picture below. Hydrogen has 4 distinct bands of light in the visible range. You have violet, bluish violet, and then turquoise green, and then red. Okay, hydrogen only produces these 4 bands in the colored range. Nothing else exists in between. How can this be? This is telling us that energy of the electrons in hydrogen can only exist at certain discrete energy levels. Okay, nothing in between. So that's why these line spectra are exactly those numbers. It can't be anything else because the energy can only exist at those levels. So the energy of an electron is quantized, just like light and energy of everything else is quantized. Okay, so then Bohr proposes that these electrons can only be found at certain levels, and they orbit the nucleus at those levels, and they don't change their levels very easily. Just like planets orbit the sun, the Earth is not going to collide with Mars. We're in our own orbits, okay? We're not going to deviate. So electrons orbit the nucleus in orbits, distinct levels, and they don't deviate, and those colors represent the orbits. So if you look at the picture to the left, Bohr assigned each orbit an energy level. Okay, and he's like saying, if the electron goes away from the nucleus, you have higher energy. If the electron goes towards the nucleus, you have lower energy. So that means in order for an electron to go away from the nucleus, that means jump to the next higher orbit, you need to absorb energy like light. Okay, and then when the electron decides to fall back into its old original orbit, that light will be released. Okay, so electrons can jump between orbits. All you have to do is provide energy. If you provide enough energy, it will jump. If you provide a lot of energy, it will skip and jump to higher orbits. But if you don't apply enough energy, the electrons don't go anywhere. You cannot be in between orbits. You can't just jump halfway. You either jump or you don't. Okay? So when electrons gain energy, it will move to an orbit farther away, and it will fall back to the original, and energy will be released again in the form of light. So the picture on the far right, you can see that the nucleus, the proton, is in the middle. You have 3 orbits with 3 different radii. Okay, and those are the 3 different energy levels. Electrons can only be found in one of those 3 levels. You're never going to find an electron anywhere else. So that's how Bohr came up with the orbits. And what about the colors? Well, the colors are produced when electrons fall from a higher orbit to a lower orbit. Specifically, red, you see red from the hydrogen. That's when electrons fell from the 3rd level to the 2nd level. So electrons fall, you release light, that light is red. When the electron falls from the 4th level to the 2nd level, it is greenish turquoise. And then from the 5th to the 2nd, you're purplish. From the 6th to the 2nd, you're pinkish purplish. All right, so those are the colors. Again, you can never be in the middle. Now, why don't we fall to the 1st level? You might have that question. Like, so how come we only ever talk about electrons falling to the 2nd level? Well, because if it falls to the 1st level, it still happens. You can release light. It's just we can't see that light. It's outside of our visible range. We can't detect it with our eyes. So we are only concerned with energy falling, electrons falling to the 2nd level. We can see those lights. That's why. Okay, you can't be in between. So if there isn't enough energy, electrons would just stay in their orbits. It's like baseball. If you want to go to the next base, you got to go to the next base. You can't be between bases. You get eliminated that way. Okay, does that make sense? And if you look at the gaps between the energy levels, the first level is really low in energy. There's a huge spike in energy to go to the second level. And then to go to the third level, you need energy, but you don't need as much energy. And the difference between the levels, the energy differences gradually decrease until it is almost non-existent. So the higher energy levels have higher energy, but you have a diminishing return. All right, so the ground state, and that word is important. Ground state means the lowest energy state for an atom. That means this atom has no additional energy. All of its electrons are in their lowest possible orbits, the lowest possible electron configuration. Only when you apply energy does it jump to a higher energy level. Now, almost all of the atoms that we're going to look at, we're going to assume that they're in ground state, okay? And you can use the analogy of stairs to better understand this. If electrons are balls and energy levels are stairs, well, you can put balls on certain levels of stairs, but you can never put it between two stairs. Okay, does that make sense? So if you move it up the stairs, you have higher energy, higher potential energy. If you learn in physics, you're higher up, higher potential energy. If you fall to the floor, you have no potential energy. So that means if you fall to the nucleus, you don't have energy. So this is a good analogy to understand the different energy levels and electrons. So do we have any questions about this? This can be a little confusing, so if you do have any questions, don't hold back and go ahead and yell into the mic. Don't be shy.
I have a question.
Mm-hmm.
So like the light, the color thing, I don't really understand. Like if a certain color hits an electron, then it will change.
Right. So, okay, so how does the color work? You will release a light with a certain color if an electron falls from a higher orbit to a lower orbit. Okay? So in the picture on the right, you can see that there are 4 electrons all falling to the second level. And they all release a different color. It depends on from where do you fall. So if you make a small drop from 3 to 2, you release red light. Well, red has low energy. Okay, red light is the weakest of all the colored lights. But if you fall from the 6th level to the 2nd level, you release a lot of energy. You release violet light, which is high in energy. So it depends on from which shell or which orbit did you fall into which one. So you create different colors. And different atoms, they have different energy levels and they're in different places. So they have their unique setup of what colored lights are produced when the electrons fall. Okay, does that make sense?
Mm-hmm.
Okay. Do we have any other questions? No? All right, so this brings us to the Bohr-Rutherford diagram. So this is the thing you learned in grade 10, and the teacher in grade 10 may have forced you to draw some of these diagrams because I forced my grade 10s to draw these. I forced my grade 9s to draw them as well. So how did we get there? Well, because you had the cathode ray tube from J.J. Thomson, you discovered the electron. And then Ernest Rutherford, using the gold foil experiment, you discovered the nucleus. And then Niels Bohr, using spectroscopy, you discovered distinct energy levels that electrons can be. So putting all of them together gives you the Bohr-Rutherford diagram. You have a nucleus. You have electrons. Where are those electrons? They're in distinct orbits around the nucleus, not found in between orbits. All right, and you may have learned that the first orbit can contain a maximum of 2 electrons. The second orbit can contain a maximum of 8, and then the third orbit also has a maximum of 8. So that's the Bohr-Rutherford diagram that we used to know. So together, Bohr and Rutherford created a fairly accurate model of the atom. So this is becoming more and more clear. Okay, now there is a maximum number of electrons each orbit can hold. We've learned that in grade 10, but we never told you why. Okay, if you asked why, I told you wait for grade 12 chemistry. Well, this is grade 12 chemistry. So tomorrow we're going to learn why certain orbits have certain maximum numbers of electrons. But tomorrow we're going to basically just unlearn everything you learned earlier. So if you don't remember grade 10 chemistry, good, forget it. Okay, this Bohr-Rutherford model that we're reviewing is not correct. Okay, everything about this is just wrong. There's no point in learning how to draw this. There is a point to get you started in chemistry and kind of understand how electrons work. But in grade 12, we're going to say, well, it doesn't work that way. So the maximum is 2, 8. Technically, the third orbit is 18, but we actually say it's 8. Again, we'll learn why tomorrow. So if you actually draw all 20, the first one is hydrogen right there. The nucleus in the middle, 1 electron. That's easy. Helium, the nucleus, 2 electrons. Okay, cool. You have 2 dots now. You put them together. You don't separate them. I see many textbooks separating those 2 electrons. Now, granted, it doesn't matter because Bohr-Rutherford diagrams are wrong to begin with, but you can be more wrong and less wrong. If you put them together, it's less wrong. If you separate them, it's more wrong. All right, so put them together, the first pair. And then the third electron, you ran out of space in that orbit. You have to start a new orbit. So that's why the first row of the periodic table only has 2 elements, because it can only contain 2 electrons in that orbit. So you start the next row, orbit number 2, 1 electron in the valence orbit for that one. So that's lithium. Beryllium has another one. So now this time you kind of separate them. You can't put them together. If you put them together, it is incorrect. And then there's boron with 3 valence. Notice I'm going clockwise. You don't have to go clockwise. Some people go counterclockwise. It doesn't really matter. Carbon has 4 valence electrons. So starting at nitrogen, you have 5. You have to now pair them. Okay, you have to put the electrons in pairs on top. It doesn't have to be on top. It could be any one, but 1 pair and 3 single electrons. Oxygen has 2 pairs and 2 single electrons. Fluorine has 3 pairs. And neon completes the orbit with 8 valence electrons, 4 pairs. So now you ran out of space. If you want to add another electron, you got to start a new orbit. Thus, you start a new row. So this is why the second row of the periodic table only has 8 elements. Okay, the third row also has 8 elements. So this also explains it. Because you have a maximum of 8 valence electrons in the third orbit, you have 8 elements in the third row. So sodium, magnesium, you have aluminum. So this is exactly the same as the row above it. The only difference is you have 1 additional orbit. So now it gets interesting. When you get to argon, you fill up the third orbit, you go to the fourth one. So potassium has 1 electron in its outer valence, the fourth shell. Calcium has 2. And then we told you don't worry about the rest. Okay. In grade 9 and 10, the students are asked to memorize the periodic table up to the first 20th element. Well, when I was in school, I have to actually memorize the first 20 elements. Now the curriculum doesn't demand that anymore, so you don't have to memorize, but you will be tested on the first 20. What is the 21st element? Most people wouldn't be able to answer that because they stop at 20. They don't care about the next one. Well, the next element is a transition metal. That's where it gets messed up. Okay, Bohr-Rutherford diagrams, they're only useful for the first 20. If you just go to Google, click images, search the Bohr-Rutherford model of anything bigger than that. Let's say bromine. You're going to look at it like, oh my goodness, I'm never going to draw that. Like, if that's on the test, I'm going to cuss my teacher. Because there are so many electrons, it's not feasible to just dot all of them. And you have to count how many in each orbit. If I'm the teacher, I'm not marking that. So that becomes very useless. So how do we represent elements bigger than calcium? well, we don't use Bohr Rutherford. This is just incorrect. Okay, this is helpful to visualize the electrons, but they're not actually like that. Electrons are not in orbits around the nucleus. There are no orbits. Bohr was wrong in that regard. There are energy levels, but there are no orbits. Okay, so the Bohr model, well, it seems promising. It offered us so much in explanation, all the light, all the colors. Problem, this is very good for hydrogen. You can determine the different colors. You can calculate the energy level. It's perfect for hydrogen. Hydrogen has one electron, though. Now, if you want to use the same strategy to study helium, you're going to quickly realize, hold on, this doesn't work. Right? The energies predicted by Bohr are not consistent for anything with more than one electron. So you only work for hydrogen on the periodic table. So there's something wrong with it, obviously. There's a flaw with the Bohr model. Okay, the flaw is that, the orbits don't exist. It's just wrong. So what is the correct model? Well, the quantum model is the most recent, most accurate model. So after Bohr, when we discovered that, hey, this doesn't really work so well, we need a better model. Well, a better model was conceived. Erwin Schrödinger was one of the scientists that realized this. Quantum mechanics is the most modern application of physics. All right, so physics, the classical physics is the easy part, Newton's law. This is the brain buster. This is utterly confusing, but this is so weird and it's true. So quantum mechanics is needed to explain what the atom looks like. And that's what we're going to learn in the next class. Now, this is the reason that we don't teach this in grade 10. You're not learning quantum mechanics in grade 10. That's just insane. That's why we lie to you in earlier grades to help you build your way up to the most accurate understanding of atom, which we will learn in the next class. Okay, so do we have any questions so far about the Bohr model? All right, I'm not hearing anything. So here is another video on the Bohr model. All right, so to cap off what we've learned, this is the timeline of the atom. You start 500 BC with Democritus, just thinking out loud that atoms are just indivisible tiny particles. Aristotle's like, hell no, atoms are actually, they're non-existent. Everything in the world is made of 4 elements: fire, air, earth, and water. And then comes the Dark Ages where no progress has been made because people die if you try. And then finally, 1800s, Dalton came up with the billiard-ball model. Atoms are in fact real and they're small and indestructible. And then you have Thomson with the plum pudding model. He discovers electrons. That means there's also protons. Rutherford, using gold foil, discovers the nucleus. And then later neutrons were discovered. Bohr, using spectroscopy and the photoelectric effect, discovers energy levels. And then later in the 1920s, quantum mechanics kicked off, and then we have a much better understanding of the atom, the quantum model. Okay, so we're gonna learn the quantum model of the atom in the next class tomorrow, and how Bohr is actually wrong. All right, so do we have any questions before we're finished?
Mr. Joe, can you go back to the slide which has line spectrum? The spectroscopy one.
All right, let me just end the recording first.
Okay.